Hello students. So the purpose of this video is to prove a single result for which a proof does not appear in the notes. And I would like to take a moment and prove that result. So I'm going to prove in particular one of the limit law claims. So I'm going to do the proof of theorem 3.1.7, claim 6. And you have the notes so you can remind yourself of what the statement is. Instead of recalling the statement of the theorem, what I'm going to do is I'm just going to set up all of the assumptions and then say the want to show. That'll tell you what I'm trying to prove. So let's give all of the assumptions. Let's let U be a subset of R, P be a limit point of U, so it makes sense to talk about limits of functions at that point P. Let's let f and g from U to R be functions. And let's assume some things. Let's assume that the limit as x approaches p of f of x is equal to L. The limit as x approaches p of g of x is equal to m. That m is not equal to 0. And that for all x in U, g of x is not equal to 0. Then here is what I claim. We want to show, so here's what I claim is true. It's the thing I'm going to show you. That the limit as x approaches p of f of x divided by g of x is equal to L over m. So there's what I'm going to prove. This will be plenty of space for the proof, this single yellow piece of paper. I'm going to go to the side and I'm going to give some motivation for how the proof will go. So off to the side in this piece of yellow bonus paper that I've just created, I will go through a proof of this argument. Or rather, I'll go through the motivation for the proof of the argument. So what is it that I want to get eventually in an epsilon delta proof? My eventual goal is going to be the function in question minus the limit in question is less than epsilon. That's what I want. So let's just take that and analyze it. So that's the same thing as f of x times m minus g of x times L all over g of x times m. Oh, need more absolute value bars. So let's take a look at this. So this piece, f of x is really, really close to L. So this is close to L times m. G of x is really, really close to m. So g times L should be close to m times L. They're both simultaneously close to L times m, so I should add and subtract that. So that's what I'm going to do in the numerator. That is equal to f of x times m minus L times m plus L times m. Maybe switch the order of the last piece just to make it look a little bit better. L times g of x all over absolute g of x times m. Now I see a variable in the denominator, which is annoying. I would rather have constants in the denominator. That would allow me to pick the thing that I need f of x minus L to be smaller than and g of x minus m to be smaller than more easily. Well, but the place where the variable is in this g of x. So let's just stare at this for a little bit. So when x is close to p, that quantity, g of x, should basically be the same as m, and in particular, it should be greater than or equal to, well, maybe strictly greater than absolute m over 2, as long as x is close enough to p. So this will now be less than, by a combination of what's written in blue to the side and the triangle inequality, that should be less than, let's look at this piece first. So there's a thing that is allegedly small, so let's just simplify that out. Absolute value of f of x minus L times m. And I'm using the triangle inequality. Oh, that's absolute m. I don't know if m is positive or negative. Plus, does this color show up okay? Yeah, it seems to show up okay. This piece is absolute value of g of x minus m. Oh, actually, it looks kind of like garbage. Times L. That should be a better shade of green, I think. And then in the denominator, g of x, sorry, that blue is not relevant. G of x is bigger than absolute m over 2. So I can replace that g of x by absolute m over 2 and make the denominator smaller, and so the whole thing bigger. Oh, neat, but f of x minus L I can make as small as I want. G of x minus m I can make as small as I want. So for now I'll just put like a box there. That's how small I can get f of x minus L times absolute m plus however small I want times absolute L all over absolute m squared over 2. Alright, well, let's just like combine things together. Those two boxes don't have to be the same, but they can be the same. But I get to pick what goes in that box. Absolute value bar, if you square, the absolute value bars don't matter, so it's just m squared over 2. So now I can decide what I want to put here. I can put any positive thing I want there, and I want this whole thing to be epsilon. So it looks like in that space maybe I'll put epsilon times m squared over 2 divided by absolute m plus absolute L. That can be simplified, but I don't need to. So there's a sketch of how the proof will go. This thing right here will get me a choice of delta. This blue bit right here will also give me a delta that I'll need to use. So there are two different choices of delta. When you see two different choices of delta, you should take the min. But let's go through those motions. So I want to prove a claim about a limit. If you want to prove a claim about a limit, you need to prove something for any epsilon bigger than 0. So let's consider any epsilon bigger than 0. Now there, it looks like, are two different places where I'll need to get a delta. So let's get both of those. So let's use that. So let's see, since limit as x approaches p of absolute, nope, no absolute value bar there, g of x equals m, there is some, and this isn't going to be the only delta that I'll use, some delta 1 bigger than 0, so that for all x in u if 0 is less than the absolute value of x minus p is less than delta 1, then absolute value of g of x minus m is less than any particular thing I want. Let's figure out what I actually want. So how close does g of x need to be to m to get this conclusion? Well, I think that it just needs to be within absolute m over 2. So let's use that. And this number right here could be any positive number that you want. I picked that number. It's definitely positive. Cool. So far, so good. And this isn't the conclusion I want, though. This is the conclusion that I want. So let's try to get that conclusion. Well, it's something about g of x, so let's study g of x. Thus, for this particular choice of x, absolute value of g of x is equal to absolute value. And I'm going to do something a little bit crafty here. That's the same thing as m minus, parentheses, m minus g of x. And there's a more, obvious way to come up with a proof of this, but I think this will be the most elegant way. Why is that a reasonable thing to do? So that's subtraction inside of an absolute value. By the so-called other triangle inequality, this is bigger than or equal to absolute value of m minus absolute value of m minus g of x. Cool. So let's play with this a little bit. As absolute value of m minus g of x is less than absolute m over 2, it follows that absolute value of m minus g of x, the thing inside of the absolute value bars in this expression, is bigger than m minus absolute value of m minus absolute m over 2, which is just absolute m over 2, and notice that that itself is positive. So absolute value of g of x is greater than or equal to absolute value of m minus, absolute value of m minus absolute value of m minus g of x is positive, so I can erase those absolute value bars. Is equal to absolute value of m minus absolute value of m minus g of x. But I just noticed that that is bigger than absolute value of m over 2. So let's just put a summary right there. Thus, for all x in u, if 0 is less than the absolute value of x minus p is less than delta 1, then absolute value of g of x is bigger than absolute m over 2. And so that bit right here corresponds to this piece that I'll need. So maybe I'll, off to the side, this isn't part of the actual proof, but you can think of that as being like part 1 of this argument. The next step comes from this red bit. So it looks like that's how close I need f of x to be to L and g of x to be to m. So let's do that. So since limit as x approaches p of f of x is equal to L, and remember the thing that we actually need, this quantity is positive. Epsilon times m squared over 2 divided by absolute L plus absolute m is bigger than 0. Yeah, that's what I want. There exists a delta 2 bigger than 0, such that for all x in U, if the absolute value of, if 0 is less than the absolute value of x minus p is less than delta 2, then absolute value of f of x minus L is less than any positive number that I pick. And I know what positive number I want to pick. I want to pick epsilon times m squared over 2 divided by absolute L plus absolute m. And I need the same thing for G. Similarly, there exists a delta 3 bigger than 0, such that for all x in U, if the absolute value of, if 0 is less than the absolute value of x minus p is less than delta, then the absolute value of f of x minus L is less than epsilon times m squared over 2 divided by absolute L plus absolute m. And now let's put all this together. I have 3 choices of delta. So let's now come up with the actual choice of delta I need. Let's let delta be the min of the lot of them. Let's consider any x in U. Let's assume absolute 0 is less than the absolute value of x minus p is less than this choice of delta. Now I'm going to try to just follow this guide, which is totally unreadable at this point, so I'll have to, partly just remember what happened. Then absolute value of f of x divided by g of x minus L divided by m. Right, let's just use what we did there. Is equal to f of x times m minus g of x times L all over absolute value of g of x times absolute value of m. And I know that this is, let's do the analyses that don't have to do with delta first. There's more than one order you can do these things in. So by adding and subtracting a single thing, this is the same thing as absolute value of f of x times m minus L times m plus L times m minus L times g of x all over absolute g of x minus m, times absolute m by adding and subtracting L times m, standard type of trick. This is now less than or equal to, using the triangle inequality, absolute value of f of x times m minus L times m plus absolute value of L times m minus L times g of x divide by absolute value of g of x times m by the triangle inequality. All right, so what did we do in the stuff way up there in the scratch walk? So maybe the next thing that was relevant to do was factor an m out of this, factor an l out of that. By factoring. Okay, carrying on. Yeah, I think I have enough space. We'll see. This is less than absolute value of f of x minus L times m plus absolute value of L, absolute value of m, L times absolute value of g of x minus m divided by absolute value of m over 2 times absolute value of m, since absolute value of 0 is less than absolute value of x minus p is less than delta 1, so absolute value of g of x is bigger than absolute value of m over 2. Cool. This in turn is less than, there's the other thing that I need. This in turn is less than epsilon m squared over 2 absolute L plus absolute m. Epsilon times m squared over 2 divided by absolute L plus absolute m times absolute m plus absolute L times epsilon times m squared over 2 all over absolute L plus absolute m. The denominator I'll just simplify. Absolute value, m squared over 2. Since 0 is less than the absolute value of x minus p is less than delta 2 rather, and 0 is less than the absolute value of x minus p is less than delta 3, so absolute value of f of x, don't even want to include that, because that choice of delta implies that f of x minus L is less than this, and absolute value of g of x minus m is less than that. That should be minus, shouldn't it? All right, well now, I'm going to take a bit of a cop-out. So I know what this should simplify down to, equals epsilon by simplifying. And maybe it's bad form for me to write off of the edge of the page, but I'm going to do so anyway. So let's see if we can justify this. Thus, for all epsilon greater than 0, did this proof start by considering any epsilon bigger than 0? Yes. There exists a choice of delta. Did we come up with a bigger than 0? Did we come up with a choice of delta? Yes, it was the min between 3 choices of delta. Why was it positive? Well, all 3 of those, delta 1, delta 2, and delta 3, were all positive. The min of 3 positive numbers is still positive. Such that, for all x in U, did I consider any x in U? Yes, right there. If 0 is less than the absolute value of x minus p is less than delta. I assume that 0 is less than the absolute value of x minus p is less than delta. So that's definitely an if in an if-then. Then, absolute value of f of x over g of x minus L over m is less than epsilon. So, the limit as x approaches p of f of x over g of x is equal to L over m as we claimed. Cool. So I'll go ahead and get this posted.